Hello everyone, welcome back to the Theory of Vibration lecture series. Today we are going to discuss about the principal coordinate, that's a principal mode on orthogonal coordinates. Um, One of the most important concepts in structural vibration, so analysis and aerospace engineering. In the previous lecture we have learned about the eigenvalues and eigenvector. Today we will build on that knowledge and to understand how complex vibration problem can be transformed into simple independent motion. This concept are widely used in the aircraft structural design, satellite vibration analysis, spacecraft dynamics, finite element analysis, machine learning through principal component analysis, that is PCA. By the end of this lecture, we will understand how engineers simplified the complicated vibration systems into independent vibration modes. Let's begin. Before moving to this topic, quickly revise some of the important concept which is related to this orthogonal things. A vector represents both magnitude and the direction. A matrix is used to perform transformation on vectors. In previous lecture, we studied the equation A pi equal to lambda pi, where A is the symmetric matrix, lambda represents the eigenvalues, and the phi represents the eigenvector. The eigenvalue tells us to the amount of scaling, while the eigenvector gives the direction that remains unchanged after transformation. The topic extended this idea. Instead of studying only one eigenvector, and we study the complete set of eigenvectors which form the principal mode of vibration. Similarly, the principal component analysis PCA uses the same mathematical concept for reducing data dimension in artificial intelligence and machine learning. Thus, the same mathematics is useful for engineers and data science. Coming to the understand of principal coordinates, imagine observing that motion of an aircraft wing that different direction. In this original coordinate system, the vibration may appear completely complicated. However, if we rotate the coordinate system, the motion becomes much simpler. These new coordinates axes are called principal coordinates. Each principal coordinate represents an independent direction of the maximum variation. Mathematically, principal coordinates are linear combination of original variables. For example, PC1 is obtained by combining all original variables using appropriate coefficient. Similarly, PC2 is another independent direction that is perpendicular to the PC1. One important property is that there is a new coordinate axis are orthogonal, meaning they are perpendicular to each other. This elimination redundancy and makes analysis much easier. Coming to the heart of the vibration analysis, unlike simple eigenvalue problem, structural dynamics involve both mass matrix M and the stiffness matrix K. Therefore, a governing equation becomes K minus lambda M multiplied by pi equal to 0. This is called the generalized eigenvalue problem. Here the K represents the structural stiffness, M represents the mass, and lambda represents the omega squared. So where omega is the natural frequency and phi is the vibration mode shape, each solution gives one natural frequency and one corresponding mode shapes. These mode shapes are known as principal mode. Every complex vibration can be expressed as a combine of this principal mode. This is exactly why modal analysis is such a powerful engineering tool that we can understand. Now coming to the conditions and the properties of orthogonality and the principal mode is in orthogonality. What does orthogonal means? Simply it is perpendicular or independent. There are three important orthogonal conditions. First is mass matrix orthogonality, where phi transport matrix M and pi equal to 0. If I not equal to j, this means different vibration modes are independent to respect mass. Second is stiffness matrix orthogonally, where phi transport k and k pi equal to 0. This indicates depends on the represent to this respected stiffness. Finally, we normalize each mode by making phi transport M pi equal to 1. Normalization simplified computation and allows each comparison between different mode shapes. Because of orthogonality, complex coupled equation became uncoupled independent equation. This greatly reduced computational effects in the vibrating systems. This concept mapped with the all the chapters which transform the original coordinate system into the independent direction. The generalized eigenvalue vectors produces the principal mode, where this principal mode satisfies the orthogonal condition because of orthogonality. Energy becomes decoupled, which makes the vibration systems analysis much simpler. These concepts are widely applied in the aerospace structures for noticing how mathematical concepts multiply engineering disciplines. Coming to the application, first application is aircraft wing flutter analysis. Engineering calculate natural frequency to avoid dangerous resonance during flight. Second application is spacecraft structural vibration. Launch vehicle experience severe vibration during takeoff. Modal analysis ensures the spacecraft surviving these loads. Another example is satellite antenna dynamics. Large antenna must be maintained precise position despite vibration. Modal analysis predicts these movements accurately. Similarly, helicopter rotor blade undergoes continuous vibration. Engineering use principal mode of improved rotor life and passenger comfort. Experimental model analysis also helps engineer to identify structural damage before it gets failure. That is how the model analysis is one of the most valuable tool in the aerospace engineering. Let's summarize today's section. Principal coordinate transform complex system into the simpler independent coordinates. Principal mode represent the natural vibration patterns of structures, where orthogonality also these modes of remaining mathematically independent. This specified vibration analysis and reducing computational complexity. These concepts are essential in aerospace, mechanical, civil, robotics, AML, structural health monitoring, and so on. I can encourage you to practice solving generalized eigenvalue problems using MATLAB and Python. It is our upcoming lecture. We'll compose more advanced applications of model analysis and vibration control techniques. Thank you. We'll see you in the next class.